And then I would like to talk about a couple of highly optimized rendering techniques based on local cube maps. We will go first through the concept of local cube maps, and then I will introduce you to a new shadow rendering technique we developed. It is a completely new shadow rendering technique based on local cube maps. It is not a solution for everything. I will explain the limitations, but it is a very efficient technique that we highly recommend for mobile devices. And then I will talk about also how to implement reflections based on local cube maps, which is also very efficient, and I also highly recommend for mobile devices. And at the end, I will discuss stereo reflections. I will discuss about the importance of rendering correctly reflections in VR, and I will show you how to do that using Unity. Why Unity? Because just I choose Unity. You should choose some platform to show how it works, and our demo Ice Cave was developed with Unity. So I will show you how to implement stereo reflections in Unity. This is something that you can get from Unity straightforward. You need to work. I will show you how to do it. So before continuing, I will show you this short video about our latest demo, Ice Cave. With this demo, we wanted to show that it is possible to achieve high visual quality content in current mobile devices. In this demo, there are more than 13 special effects running at the same time. So I will show you just a short video, but I encourage you to visit our booth and you will experience yourself with the Samsung Gear VR.
An abandoned cave, home to an ancient lunar calendar, used at one point in time as a site for celebration. In the distant past, people would climb the mountain up to the glacier cave, and after paying their respects, rotate the statues of the zodiac animals around the calendar board. No one has visited the cave for thousands of years, but the spirit of the past is still alive.
So I hope you enjoyed the video. And sorry. Let's continue with the talk. I would like to concentrate in a couple of highly optimized rendering techniques based on local cube maps that we use in this demo. And one of them was specially developed for this demo. That is the shadows based on local cube maps, which is a completely new rendering technique. As you know, shadows are difficult, are expensive to implement in mobile devices. And for VR, it is a performance killer. So using efficient shadows technique for VR, it is important. But before introducing those techniques, shadows and reflection based on local cube maps, I would like to go through very shortly the concept of local cube maps. And I will introduce the concept of local cube maps independently of the use we make of it. So let's assume we got some local environment delimited by some boundary, and we got some red star in the boundary, and we are looking to the red star in the direction of the vector v. And we have baked a cube map from some point inside of our environment. And the question is, what is the vector we need to use to get the star when we fetch the texture from the cube map? What is that vector? If we think about, we can use the vector v. So if we use the vector v, we will get something else, because the vector v is pointing to some other direction in the boundary of the local environment. So what is that vector? If we look carefully, so we need to think that that vector should have the origin in the position where the cube map was generated, and it must finish in the position where the vector v intersects the boundary of our local environment. But if our boundary is arbitrary, how we can find the intersection of this vector with the boundary? We necessarily need to simplify the problem. And to simplify the problem, we use a proxy geometry. And the simplest proxy geometry we can use in this case is the bounding box of the scene. It is very easy to find the intersection point of a vector with a bounding box. And the problem is even simpler if that vector has the origin inside of the bounding box, which is this case. So we find the intersection point of the vector with the bounding box, and we build a new vector from the position where the cube map was generated to this intersection point. And that is the vector we need to use to fetch the texture from the cube map and get the red star. So when we are dealing with a local environment, when we are working with cube maps in the local environment, we need to use the concept of the local cube map, which is a little more complex than the simple standard cube map. The local cube map is compounded by the standard cube map, but you need to consider the cube map position, you need to consider the scene bounding box, and you need to apply the local correction. It means you need to find the intersection of your vector with the bounding box and build a new vector from the position where the cube map was generated to this intersection point. And that is the vector you need to use to retrieve the texture from your cube map. And this you need to do always when you are working in a local environment. You don't need to apply the local correction, and we call that local correction, only when you are using the cube map from a very distant environment, when you are using the cube map, for example, as the skybox. Why? Because in this case, the local corrected vector and the vector without any local correction will be the same. So let's see now how we could implement, let's introduce this new shadow rendering technique based on local cube maps. So this technique works in two stages. During the first stage, we baked the cube map, we rendered the cube map, but we rendered the cube map in such a way that we rendered the transparency of the boundaries of our scene in the alpha channel of the cube map. If when rendering the cube map in the alpha channel, we are rendering some opaque geometry, we write 1 in the alpha channel. If we are rendering a completely transparent geometry, or there is no geometry, we render 0. For example, when we are rendering the window, which is there, we write 0 in the alpha channel of the cube map. At this point, we are not considering the position of the light, or we are not considering the number of the light. So this method will work for any number of light and for any position of the light. The only restriction is that the light should be outside of the bounding box that delimits our local environment. So let's see now how this technique works at runtime. So at runtime, in the vertex shader, we need to build a vector. We need to build a vector from the vertex to the light position. So we got the vertex to light position vector, and we pass that vector to the fragment shader as a varying, in such a way that this vector will be interpolated. And in the fragment shader, we will have a fragment to light vector. But as I explained before, we will use that vector to fetch the texture from the cube map, but we can't use that vector directly. We need to apply the local correction to that vector. We need to find the bounding box of the scene, and we need to find the intersection point of that vector, the fragment to light vector, with that bounding box. And then we need to build a new vector from the position where the cube map was generated to this intersection point. And that is the vector we need to use to fetch the texture from the cube map. When fetching the texture from the cube map, we are interested only in the value in the alpha channel. If we fetch a value from the alpha channel 1, it means that in the direction of the fragment to light vector, there is an opaque geometry. It means that the light can't reach that fragment, and that fragment will be in shadows. If when retrieving the texture from the cube map, we get 0, it means that in the direction of the fragment to light vector, there is no geometry, or the geometry is completely transparent. It means that the light can reach that fragment, and that fragment will be lit. As simple as that. The implementation of this technique is just one fetching of the texture from the cube map and a couple of lines for finding the intersection point. I will point you at the end where you can find the source code of the shader. We can't go now because we don't have enough time to go through that, but it is already published. This technique also can reproduce the softness of the shadows. So the shadows are softer the farther away they are from the object that create the shadows. And I will show you with a short video in seconds. So how we do that? When we are baking, when we are rendering our cube maps, we also produce the cube map min maps. And at runtime, we use a parameter which is proportional to the distance from the fragment to the intersection point to interpolate between cube maps in such a way that we get the farther away the fragment is from the intersection point, the more blurred would be our texture. This short video shows how the shadows are automatically updated when the light is changing the position, and also when we change that parameter. As you can see there, the shadows can vary from very hard shadows to very soft shadows. I will really encourage you to come to our booth because I got that demo in a tablet and you can play with it. So this technique is based on static local cube map. So you render the cube map offline. And the question is, what happens if in your scene there are some dynamic objects? Of course, this technique won't work for those dynamic objects because you have rendered your cube map offline before. So in this case, what we do, and as we did in the demo, we render in our shader the shadows from the static geometry, the geometry that doesn't change during in time from our scene, and we render the shadows from dynamic geometry using other standard rendering, shadow rendering techniques, for example, shadow mapping. And then in our shader, we combine both types of shadows in a single shadow picture. This is what we did in the ice cave demo, where the shadow from the dynamic objects, for example, the phoenix, which is in the center of the platform, has been rendered using shadow mapping technique, which is rendered to a texture every frame. and the shadow from the static geometry, the wall of the cave, where the light can come through a big hole in the top and from the entrance of the cave. Those shadows are rendered using the local cube map technique. I have to say also that when working with this new shadow rendering technique, which is based on local cube map, as we every frame fetch the texture from the same cube map, we don't have any pixel shimmering or pixel instability that we see when we are using other rendering techniques, for example, shadow mapping, because those techniques render to a different texture every frame. And then in the border of the shadows, you always see some flickering, some pixel instability. So this technique can give you not only very efficient shadows, but also high quality shadows. Let's see now how we can render reflections also based on local cube maps. So as you probably know, if we need just in our shader to supply the view direction and know the normal to the reflected surface, and automatically you got a function that will give you the reflection vector. When we are working with reflection based on local cube map, this time when rendering the cube map, we render in the RGB channels the environment. So we use the RGB channels of the cube map. But when fetching the texture, we can't use the reflection vector as it is. We need to apply the local correction. It means we need to find the intersection point of the reflection vector with the bounding box of the scene and build a new vector from the position where the cube map was generated to this intersection point, and which is there as R prime. And this is the vector R prime that we use to fetch the texture from the cube map. And that only in that case we will get the right reflection. In the ice cave, we combine three different types of reflections. The reflection from the static geometry, from the wall of the cave, has been rendered using the local cube map technique. The reflection from the dynamic object, in this case the phoenix, the butterfly which is flying somewhere there, are rendered using the mirror camera technique. So for example, if our main camera is looking to this surface, which is the reflection surface, so we place a mirror camera from below, pointing from some position that we need to calculate, and we need also to set the right orientation to render the wall upside down, and then we render that to a texture, and we use that texture rendered at runtime to render the reflection from dynamic objects. And also in the demo, we rendered the reflection from the skybox, which is a very distant environment, and in that case we just use the cube map as it is. We don't apply any local correction to the reflection vector. And we combine all these three types of reflections in a single reflection picture. And this is, I'm just showing there the different type of reflections that we have used in our demo. So now I would like to discuss a little about the importance of rendering stereo reflections when we are in VR. The point is that, and it happened to us, it's based on our experience. When we initially our demo wasn't a VR demo. We moved to VR. We were working in Unity. We moved to VR. It was very easy to move to VR, as you know. Those of you which are familiar with Unity. But the point is that when you are rendering to a texture in Unity, that texture, the same texture, is used for the left and the right eye, and where if your reflections are relevant in your wall, as it is the case, because we got a big platform with a lot of reflections there, the user will spot it very easy that there is something wrong in the wall. I mean, the reflection doesn't fit correctly the object which are reflected on the reflected surface, and we had that problem. And this doesn't help to keep the sense of immersion of the user. We want the user to believe that he is really there inside the wall. But the point is that if the user sees something wrong, it will spot it very easy that the reflections are not right, and that won't help us to deliver a best quality of user VR experience. So let's see how we can implement stereo reflections in Unity. So the first step is to create two cameras that will be responsible of rendering the reflection from the left and from the right eye. We create those two new cameras, but we need to disable them because we will handle their rendering manually. We need to render them manually because we need to be in sync. We need to be synchronized with the main camera. So we create the two cameras, we create the target, the cameras will render to, and we will attach this short script to each camera. For those of you which are familiar with Unity, the onPreRender function is a callback, which is called by Unity just before the camera will render. And the onPostRender is called by Unity just after the camera finishes the rendering. The setup camera, because I don't have enough room there, but I will point you to a blog at the end where you can find the implementation of the setup camera. The setup camera function just places your mirror camera in the right position and with the right orientation to render correctly the reflection for a given main camera. Okay? When rendering reflections using a mirrored camera technique, we render the wall upside down. So we need to invert the winding of the geometry. And we need to restore the winding of the geometry as soon as we finish rendering with the reflection camera. So this is what we need to do with the reflection cameras, which are responsible for rendering reflections for the left and for the right eye. Let's see now what we need to do with the main camera. The point is that we need to synchronize our reflections camera with the main camera. So and again, we are using here in this script the onPreRender callback of Unity. This function is called by Unity twice every frame, just before the main camera starts to render your frame. So the first time it is called, it's for the left eye. So in this part, when the eye index is 0, we call the rendering of the left reflection camera. We get the texture the camera has rendered to, and then we update in our shader that texture. And the second time is called, then we render manually right reflex camera. We render the right reflection camera. And again, we update the texture in our shader. So we get, I will show you here, this is what, when I was developing this method, I needed to know if I was in sync, if the rendering of the reflection camera were synchronized when the main camera was rendering for the left main eye, and then when the right main eye. So I just passed to the shader the eye index, and for the left eye index, I use a red texture, and for the right eye index, I use a green texture. And this is a picture that I took from the device, just to show that I was getting a stable picture. So I was in sync. Both left and right reflection camera were in sync with the left and right main camera eyes. And this is what we got. It's not possible to notice here, but I will really encourage you to go to our booth and try in VR with the headset, and you will see that the reflection match perfectly with the objects which are reflected on the platform. And this is all. Let's wrap up. Shortly, we have seen that a couple of highly optimized rendering techniques based on local cube maps. So we can use the local cube map technique to render very efficient shadows and reflections for the static geometry. But for the dynamic geometry, we can use other techniques, well known, and we can combine them at runtime to get a full picture of shadows and reflections in mobile VR. Finally, when dealing with reflections in mobile VR or in VR in general, we need to render stereo reflections. And in this link, which is there, you can find the complete source code for everything. It is a blog I released recently before giving this talk at GDC. So finally, I will encourage you to go to our website and download the ARM guide for Unity developers, where you can find a detailed description of all the special effects that I show you in the video. So now we have some.
Yes, we have some time left for questions and answers. So any questions, guys? Anybody? Just raise your hands. Perfect.
Hello, thank you for your speech. So my question is, you're using large textures on mobile devices. You basically use cube maps, and they take a lot of space. So what are the limitations?
Okay, the size of the texture we are using here is 512, but in current device, texture are not already a problem. It is the bandwidth which is the problem. So 512 is not a big texture. We are using that texture to render the shadows. For shadows, we are using also that texture to render reflections. It's not a deal, believe me. In the current mobile devices, I'm talking about S6, for example. We are running this demo in S6, Galaxy S6, which is not the last one. This is not a problem. The current mobile devices has a lot of memory. The problem in the devices is the bandwidth. Every time you transfer some data from your video memory to the main, CPU memory. But no, it's not a problem. It's not a real problem. Of course, it depends how many, how much. Yeah, you're using. If you're using, I don't know, 2 gig of memory or whatever. But no, it's not a problem. Right now, it's not a problem. The handling a lot of texture in your game. Roberto?
Yeah. Thank you for an amazing presentation. I just wanted to ask how to handle the multiple lights for your shadow techniques, and again, like approximately how many lights you can make shadows from.
You can use this technique for as many lights as you want, but you know that using real lights in your games has a limitation. Most of the lighting effect you baked, and in texture, most of the lighting effect. But this technique can be used in principle for any number of lights. The point is that you need to, the procedure I described there, applying the local correction to the vector, you need to do for any light. So you need to find the vertex to fragment, the vector to light source vector for any number of lights, and repeat the procedure for every light. But you can, and I did, in the current demo, I'm not showing this because when you have more than one light and you have a lot of shadows, it is really difficult to distinguish which shadows is coming from which light. But yeah, it's not a problem. You can use this method to render the shadow from any number of lights.
Okay, guys, so that's pretty much it. We're running out of time, but I believe that Roberto will be pleased to answer your question after this lecture, right?
Yeah, I will be there in my booth, so please come there.
Amazing, so big applause.
Thank you very much. Thank you.